We're now going to solve a differential equation, and what we do to solve one is to let v equal to y over x. Remember, we can get dy dx as a function of y over x. We let v equal y over x, y is equal to vx. We take the derivative with respect to x, get dy dx is first times derivative of the second, which is v times 1, plus second x times the derivative of the first, dv dx. So we take that for dy dx and replace it. We have the function of xy now as another function of y over x. We replace dy dx with v plus x dv dx and take the v to the other side, right there, that minus v. So now we have it in a form that I think you can see. It's going to be easy to get it variable separable. We divide both sides by g of v minus v and multiply by dx over x. And we have this form that's ready to integrate. So it's a simple variable separable to solve a given homogeneous differential equation.
Let's look at this equation that's a first order DE in differential form, and it's of homogeneous type.
The first thing we're going to do is get this differential equation in the form dy dx is equal to a function of x and y. As you see here, we moved the 3x minus y squared to the right-hand side and made it y squared minus 3x squared, then divided by the xy minus x cubed over y. So we have a function of x and y. Now we're going to test this for homogeneity by replacing x with tx and y with ty, and we get the form that you see right here. In the numerator, we can factor a t squared. In the denominator, we have a t squared. Here we have a t cubed over t, which is t squared, which we can factor in the denominator. Those go out, and indeed we have a function of xy. So it is homogeneous. Or if you want to divide numerator and denominator by x squared, that's probably the best thing to do because we're going to need to get it in the form that you see there on the right. If we divide by x squared, you can see we have y over x quantity squared minus 3, y over x minus 1 over y over x. So we do have a function of y over x, and what we're going to do is let v equal y over x, or y equal to vx, and again we get what I mentioned at the beginning here, dy dx, first times derivative of the second plus second times derivative of the first. We replace y prime with v plus x dv dx, and we replace the y over x with v, and we get the form that you see right here. Then in this next step, we've multiplied both sides by v minus 1 over v. We multiply this, and notice we have a v squared minus 1, we have a v squared minus 3. The v squares go out. We bring the minus 1 over with the minus 3 and get a minus 2, and we divide both sides by x. And we have the variable separable here. We also multiplied by dx there and got dx over x. So we have a variable separable. We can integrate v dv and get v squared over 2. Minus dv over v is minus log absolute value of v. Minus 2 over x, we get minus 2 log absolute value of x, and we add our constant of integration there. Now if we bring the log of absolute value of v to the right-hand side and write this as log of x to the minus 2, we get log of absolute value of v over x squared plus a constant. Now we're going to take the analog, or exponentiate, e to the log to the base e of magnitude of v over x squared is just the magnitude of v over x squared, and we get e to the v squared over 2 times e to the minus c1. We take this e to the minus c1, we're going to replace it with a c, and we put a plus or minus in here because that will take care of the absolute value. So we simply get v over x squared is equal to a constant e to the v squared over 2. Now replace v with y over x in both of these spots, and we have the form that you see right here. Y over x squared is equal constant e to the y squared over 2x squared. Then if this is y over x squared, so it's really y over x cubed. If we multiply both sides by x cubed, we get our final result here of y is equal to a constant times x cubed times e to the y squared over 2x squared.